Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about a quarter pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide a resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation, drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here, it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. Every year, over 1 billion feet of steel chains are produced worldwide, from those that lift sea cranes to those that support bridges. But only a few of them go through a journey where precision is measured in microns, and every spark during welding is the beat of a metal heart. Imagine, a piece of ordinary steel transforms into a link capable of withstanding tens of tons. How exactly? In a few minutes, you will see how a force that cannot be broken is born. And if you watch until the end, you'll learn the secret that determines whether a chain will survive under maximum load. Our journey begins not in the noisy workshops, but much earlier, in the design office. It is here, at the design stage, that engineers determine what our chain will be like. What is it intended for? What loads must it withstand? Will it operate in an aggressive environment? The answers to these questions dictate the choice of material. In the vast majority of cases, for the manufacture of welded chains used in lifting mechanisms, industry, construction, or as fastening elements, we use high-quality steel rod. Take a look at these warehouses. Here they are, our round bars, thick, heavy, shining with strength. They can have different diameters, from a few millimeters for light chains to tens of centimeters for true giants that lift tons of cargo. Each batch of rods undergoes a thorough incoming inspection. The metallurgical laboratory checks the chemical composition of the steel, its mechanical properties, tensile strength, impact toughness. This is critically important, as the safety and reliability of the final product depend on the quality of the raw material. Only rods that meet the highest standards are allowed for further processing. This is the first, but extremely important, step in ensuring the unsurpassed quality of our chains. So, our selected steel rod is ready for transformation. The next stage is cutting. Here, high-precision cutting machines come into play, which, like surgeons, cut long rods into sections of a perfectly specified length. These sections will become our future links. Every millimeter matters, as the uniformity and correct geometry of the entire chain depend on the cutting accuracy. Operators carefully monitor the process, controlling the dimensions of each blank. And now we move on to one of the most spectacular stages: forming the link. Look at this powerful machine. It's an automatic press or a special bending unit. The metal section, heated to a plastic state, and sometimes without preheating if the diameter and steel grade allow, is fed inside, and under colossal pressure or a complex bending motion, it is transformed. Before our eyes, a straight rod is bent into a perfect oval or round shape, the future link. It is important that the ends of the rod are not completely joined, leaving a small gap, a seam. This seam will be a key element for the next stage. The newly formed link is fed to a mechanism that threads it through an existing link of the chain. It's like an amazing dance where one part is woven into another, creating a single whole. And now, the most important moment: welding. Most often, electric resistance welding, or flash butt welding, is used for chains. This is a high-tech process where the ends of the link that form the seam are clamped between electrodes. A powerful electric current is passed through them, which instantly heats the metal to its melting point. See those bright flashes? The fountains of sparks? That's the metal melting. And then under the pressure of the electrodes, an upset occurs. The ends are joined, forming a strong, homogeneous weld. In some cases, especially for very large chains, arc welding may be used, but the principle remains the same, creating an unbreakable metal joint. This weld is not just a connection. It's the weakest point of the link, and it is here that its future strength is established. Welding masters are true virtuosos, as the integrity of the entire chain depends on their work. After welding, the excess metal can be trimmed or processed for smoothness. The newly formed and welded chain, although strong, has not yet revealed its full potential. To meet the highest requirements for strength, durability, and safety, it goes through a series of finishing processes. The first of these is calibration. The long chain passes through special dies under pressure. This ensures the precise dimensions of each link, eliminates minor deformations after welding, and gives the chain uniformity. A calibrated chain will be ideal for working with sprockets and other mechanisms where precision is critical. After calibration, the chain heads to the heart of the factory: heat treatment. This stage is one of the most important and determines the final mechanical properties of the chain. Depending on the steel grade and desired characteristics, the chain may undergo several operations. Let's talk about each of them separately. Quenching. The chain is heated to a high temperature in special furnaces and then rapidly cooled in water, oil, or a polymer solution. This makes the steel very hard but brittle. Tempering. To eliminate the brittleness after quenching and increase the ability to absorb impact energy without breaking, the chain is heated again, but to a lower temperature and cooled slowly. This process gives the chain the necessary balance between hardness and ductility, normalizing. Sometimes, instead of, or in addition to, quenching and tempering, normalizing is used, heating to a certain temperature, followed by cooling in air. This improves the metal's structure and relieves internal stresses. All these processes are carefully controlled by computer systems, as even a small change in temperature or holding time can significantly affect the final result. Heat treatment is a true art of controlling the properties of metal. After heat treatment, the chain comes out of the furnace, but its journey is not yet over. At this stage, it may have scale on it, a layer of oxides formed at high temperatures. Therefore, the next step is cleaning. This usually happens in special shot blasting chambers. Thousands of small metal shot particles under high pressure bombard the surface of the chain, knocking off scale and other contaminants. The result? The chain becomes clean, smooth, with a pleasant metallic sheen, ready for the next stages. In order for our chain to serve long and reliably even in difficult conditions, it needs protection from corrosion. This is where coating comes into play. The most common method is galvanizing, which can be hot dip or electroplating. In hot dip galvanizing, the chain is immersed in a bath of molten zinc at a temperature of 860 degrees Fahrenheit. Zinc, interacting with steel, forms a strong protective coating that not only prevents rust, but also has the property of self-healing for minor damages. In electroplating, the chain is placed in an electrolytic solution, and under the action of an electric current, zinc deposits on the surface of the steel. This coating is thinner, but gives the chain a more aesthetic appearance. In addition to galvanizing, other types of coatings may be used. For example, polymer paints, or special anti-corrosion compounds, depending on the purpose of the chain. We are approaching the final stage, and this is perhaps the most responsible moment: testing. It is here that our chain confirms its readiness to perform the most complex tasks. Every single chain undergoes a whole complex of checks for compliance with international safety and quality standards. Look at this huge test stand. Here the chain is subjected to colossal loads. It is stretched with a great force, which significantly exceeds its nominal working load, but at the same time does not reach the breaking point. This is the so-called proof load test. During this process, possible hidden defects and weak points that could manifest during operation are revealed. If the chain successfully passes this test, it means that it will withstand the declared loads and ensure safe operation. In addition to this, other types of control are carried out. Specialists carefully inspect each link for cracks, deformations, quality of welds, and coating. With the help of special calipers and measuring instruments, the compliance of the link sizes, their shape, and the chain pitch with the specified parameters is checked. From each batch of chains, samples are taken, which are then subjected to breaking tests. This allows to determine the maximum breaking force that the chain can withstand and to make sure that it meets or exceeds the established norms. These are brutal but necessary tests that guarantee that the entire batch of products is reliable. Only chains that have successfully passed all stages of quality control without exception are given the right to leave the factory premises. Each batch is accompanied by a certificate of conformity, which confirms its characteristics and the passing of all tests. This is our guarantee, a guarantee that you are getting a product of the highest quality and reliability. And now, dear viewers, we see the final result. Chains of different sizes, diameters, with different coatings, neatly laid in coils, ready to be sent to all corners of the world. They will go to the construction of skyscrapers, to port cranes, to ships, to agriculture, to production lines, everywhere where unbreakable strength, reliability, and safety are needed. From small, elegant chains for decorative purposes, to huge ones that lift bridges, each of them has gone through a long and complex path of transformation, from raw metal to a high-tech product. Every year, over 400 million tons of paper are consumed worldwide. That's more than the weight of all the airplanes ever built by man. But have you ever wondered where this white sheet, on which we write, print, or package goods, comes from? It all begins with raw wood, which machines strip of its bark, shred into even chips, and send to giant boilers, where pressure and temperature transform the solid log into delicate cellulose fibers. This is not just production, it's the alchemy of modern times. And at the end of the video, I will reveal a secret that will change your perception of paper forever. The preparation of raw materials for paper production is a very important and interesting stage that lays the foundation for the quality of all the paper we later get. It begins with bringing the wood into a state convenient for further processing. First, large timber is delivered to the paper mill, where it is debarked. The reason is simple. The bark is not needed. It contains many impurities that spoil the quality of paper and create problems during cooking. To remove the bark, special machines, debarkers, are used. These are large rotating drums or hydraulic systems that, like real tigers, strip the bark from the wooden logs without damaging the wood itself. It's like a thorough scrub for the wood. The amount of bark can reach 15% of the log's weight, so removing it is not just necessary, but it also significantly improves the subsequent process and the final quality. After cleaning the wood from the bark, it is shredded into small pieces, which in the paper industry are called chips. Special mechanical chippers are used. These are machines with a large number of sharp knives that quickly and evenly cut the logs into small chips, approximately 1 and 2 inches long. It's like chopping firewood in half, only on a much smaller scale. It is important that the size of the chips is as uniform as possible. If the pieces are too large or uneven, then during the next stage, cellulose cooking, individual parts will be processed unevenly, which will affect the quality and strength of the paper. Therefore, the chippers are adjusted to maintain maximum stability of the chip size. Immediately after shredding, the chips are fed into cooking boilers. But before that, they are often moistened or slightly steamed to facilitate the softening and dissolution of wood components, such as lignin. These steps also improve the energy-saving characteristics of the process. One of the tricks is that the bark contains various minerals and substances that can contaminate the cellulose, create problems in chemical reactions, and disable the equipment. So, thorough cleaning helps not only to get a cleaned raw material, but also makes the cooking process more stable and of higher quality. Thus, how clean and strong the cellulose mass will be depends on the removal of the bark and the shredding of the wood. To make one medium-sized roll of paper, you need to process several hundred pounds of wood, so every step in the preparation is very important. After the wood in the form of chips enters the huge boilers, it is placed in special reactors, where it is boiled in an aqueous solution of a sulfuric lignin-removing alkali. Most often it is caustic soda and sodium sulfide. Usually, the cooking temperature reaches about 300 degrees Fahrenheit, and the pressure can exceed 15 atmospheres for the process to be effective. The chemical reagents dissolve lignin, the substance that glues the wood fibers together. At the same time, the wood fibers remain practically undamaged, which is important for the quality of the future paper. At the same time, other undesirable components that can affect the color, strength, and texture of the paper are also removed. This process is called sulfate, or craft cooking, and it ensures the production of the strongest and cleanest cellulose among all methods. For different types of paper, the proportions of chemical substances, the time, and the cooking temperature may differ, depending on the type of raw material and the required quality of the final product. After the cooking is complete, the cellulose suspension is cooled, washed to remove the remaining reagents, and sent for further cleaning, removal of residual impurities, and refining. To eliminate the foam that forms during this process, special defoamers are used. After cooking the cellulose, when most of the lignin has already been removed, the paper mass usually has a yellowish or brownish tint due to residual impurities. This is where the bleaching process comes into play. Bleaching is designed to make the cellulose white or as light as possible, which is especially important for printing paper, colored cardboard, or high-quality office products. Most often, modern chlorine-free bleaching technologies are used, which are more environmentally friendly and do not form dangerous organochlorine compounds. Chemical reagents, such as hydrogen peroxide, ozone, sodium dithionite, or oxygen, gradually oxidize or reduce the colored components, thus lightening the mass without destroying the fibers themselves. In general, this is a fine balance, as too aggressive bleaching can worsen the strength of the paper. In addition to bleaching, at this time, deep cleaning of the cellulose suspension from small impurities, residues of paint, metal particles, resins, which can affect the color and quality of the product, takes place. For this, flotation units are used, where impurities, due to the difference in specific gravity and surface properties, are separated from the mass and removed. After this treatment, the cellulose mass becomes light, clean, and homogeneous, ready for the next stage of forming thin paper sheets. The formation of a paper web is the moment when the cellulose mass, consisting of fibers and water, becomes the paper itself. The process takes place on special equipment, a paper-making machine that has a processing screen. The cellulose suspension is evenly distributed over a large metal screen, which continuously moves forward. Through the openings of the screen, water begins to drain down, reducing the moisture in the paper mass. The fibers, in turn, are retained and begin to form a thin but strong layer. This thin layer, the future sheet of paper, continuously moves together with the screen to a complex of presses and drying rollers. Here, the remaining water is finally squeezed out. The paper is heated and acquires the required density and texture. After completing these stages, the thin and strong sheet of paper continues its journey to layer-by-layer processing and cutting. After forming a thin layer of cellulose mass, the process of pressing and drying begins. First, the paper sheet passes through the press section of the machine. Here, 2 or 3 heavy rollers press the thin layer, squeezing out the excess water. It's similar to wringing out a wet cloth. Pressing increases the density of the paper and prepares it for the next step. The moisture after the press is reduced to about 45%. Next, the sheet moves on to the drying rollers, large cylinders heated by steam, the temperature of which can reach 300 degrees Fahrenheit. The paper passes between these rollers, and the heat quickly evaporates the remaining moisture. The moisture exits through the open pores of the paper and drains into a condensate collection system. This stage is very dynamic. The paper sheet can move at a speed of several hundred meters per minute, quickly drying, but at the same time retaining its flexibility and strength. After drying, the paper becomes strong, smooth, and ready for further calibration and cutting. If necessary, the sheets pass through calendars, mounted pairs of rollers that give the paper a smooth shine and even thickness. After drying, the paper sheet passes through a pair of large, heavy, and very fast-rotating steel rollers. This is called a calendar. These rollers press on the paper with great force, literally rolling it, to even out the thickness and give it a shiny surface. The temperature of the rollers can be very different depending on the type of paper, from about 80 degrees to over 500. The heat helps the fibers to melt a little, which improves the smoothness and strength of the web. With the help of calendaring, the paper becomes denser, more uniform in thickness, and also better suited for printing, as the ink lies on such a surface evenly and richly. The final stage of paper making is cutting and packaging. The finished paper roll, or a long ribbon, is fed to automatic cutting machines, where it is cut into sheets of standard or individual sizes, depending on the needs. For this, guillotines are used, large mechanical scissors that make an even and precise cut simultaneously across the entire width. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. And the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these 3 products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Today, we're embarking on a journey to one of the coolest and smartest factories in the world of woodworking. We're going to talk about how people looked at ordinary wooden floors, which fear moisture like a vampire fears garlic, and said, "Dude, we can do better." Thus, engineered hardwood was born. This isn't just a board, it's a true wooden club sandwich, a brilliant work of engineering where the beauty of natural wood is combined with superhuman stability. This is the story of how a floor that laughs in the face of humidity fluctuations is born from several different trees, a giant glue juicer, and an infernal ultraviolet tanning session. It all begins not with one, but with two different forests. The first forest is a runway for supermodels. Here grow those noble trees whose beauty makes the heart beat faster. Majestic oak, strong hickory, elegant maple, or luxurious American walnut. For our sandwich, we don't need the whole log. We only need its soul, its most beautiful part, the thin top layer that everyone will see. Therefore, the best, straightest logs are brought to the factory. First, a real spa day awaits them. They are immersed in huge pools of hot water, or placed in chambers where they are treated with steam at a temperature of 200 degrees Fahrenheit. This is done to soften the wood and make it ready for the thinnest slicing in the world. After this, the log goes to a machine that is something between a giant pencil sharpener and an industrial slicer for delicacies. This is a peeling or slicing machine. Imagine a sharp, scalpel-like knife 10 feet long. It is slowly brought to the rotating log and begins to shave off a continuous wide ribbon of wood, just 1/8 or even 1/16 of an inch thick. This is our veneer, our precious ham for the sandwich. This wet, flexible sheet is then carefully dried in special chambers to make it stable, but to preserve its natural beauty. But what will be the bread in our sandwich? For this, we don't need supermodels. We go to another forest where simple workhorses grow. Fast-growing and inexpensive species like poplar, birch, or eucalyptus. These logs go through a similar peeling procedure, but the ribbons are cut a little thicker. And this is where the main secret of the stability of engineered hardwood begins. Imagine that you took several of these thin wooden sheets. You lay the first one so that the fibers run lengthwise. You lay the second layer on top, but you turn it 90 degrees so that the fibers run crosswise. The third, again lengthwise. The fourth, again crosswise. And so on, creating a multi-layered pie where each layer is perpendicular to the previous one. Why is this so important? Because wood is alive. It always tries to expand and contract across the grain, reacting to humidity. But when you glue these layers perpendicularly, they seem to hold each other in a steel embrace. One layer wants to expand, but the other, lying perpendicularly, does not allow it to do so. This is a brilliant solution that makes the base of engineered hardwood incredibly stable and resistant to deformation. This multi-layered pie of cheap wood is sent under a hot press, where under huge pressure and temperature, it is glued into a single, strong block, like plywood. These are the muscles of our floor. Now it's time to assemble our club sandwich. We have the sole, a thin, beautiful veneer of expensive wood. And we have the muscles, a thick, stable base of cheap wood. They need to be connected. The base moves along a conveyor and passes under rollers that resemble giant paint rollers. These rollers generously pour a special, incredibly strong glue onto it. Our precious veneer is carefully laid on top of this sticky surface, and this whole structure is sent to the final hot press. With a force of hundreds of pounds per square inch, the press connects beauty and strength into a single hole. At the exit, we get a huge master sheet, from which individual boards will then be cut. But this is not a floor yet, it's just a blank. It's time for makeup and a manicure. Giant saws cut the large sheet into individual boards of standard width, for example, 5 or 7 inches. And here, each board goes to one of the most important machines, the milling machine. An incredibly complex system of mills and knives, rotating at a frantic speed. On one side of the board, they cut a long protrusion called a tongue, and on the other, an equally long groove called a groove. It is this system that will allow the boards to fit together perfectly during installation, forming a continuous, smooth surface without gaps. Now our board has the correct shape, but its surface is still a bit rough. It is sent for sanding. This is a whole line of several sanding machines, each of which uses finer and finer sandpaper. After this process, the surface of the board becomes as smooth as silk, ready for the final coating. And here, the real high-tech begins. The board enters a finishing line that looks like a car wash, only instead of water and soap, there is varnish and ultraviolet light. First, rollers apply the first layer of a special, incredibly durable varnish based on aluminum oxide. This is one of the hardest substances in the world, which makes the floor resistant to scratches. Immediately after application, the board passes under powerful ultraviolet lamps, And the varnish, which in normal conditions would dry for hours, hardens in a fraction of a second under the influence of ultraviolet light. Then a second layer is applied, and again a tan under ultraviolet light. The third, fourth, fifth. Sometimes it goes up to 7 to 9 such layers. As a result, we get a perfectly smooth, incredibly strong, and durable coating. That ultraviolet coating is not just a varnish. Aluminum oxide is added to its composition, one of the hardest minerals in the world, second only to diamond. From 7 to 9 layers of this coating are applied to the board, and each layer is instantly baked by ultraviolet light. As a result, we get a surface that is many times more resistant to scratches and wear than a traditional varnish applied to a solid board after installation. At the final stage, each board undergoes strict quality control. Inspectors with an eagle's eye look for any defects, scratches, uneven color, problems with geometry. Only perfect boards get a ticket to life. Robotic manipulators carefully stack them in boxes, indicating the type of wood, color, and dimensions. And so, having passed the path from 2 different forests, through hot baths, sharp knives, sticky waterfalls of glue, and an infernal ultraviolet tan, this brilliant creation is born, engineered hardwood. It took the best from nature, its beauty, and the best from engineering, its stability, to become the perfect floor for our homes, which is not afraid of either winter dryness or summer humidity. The engineered hardwood market in the USA is a giant that turns over more than $10 billion a year. And this is not just a stable market, it is growing rapidly, winning an increasing share from its older, solid brother, solid wood. Why? Because it's smarter, and the numbers prove it. The main superpower is stability. Thanks to its cross-layered, multi-layered structure, engineered hardwood is 50 and even 60% more stable than a solid board of the same species and thickness. What does this mean in real life? It means that it can be installed where ordinary wood would go crazy from humidity fluctuations, in basements, kitchens, bathrooms, and on a concrete slab. It is not afraid of underfloor heating. If one perfect log of precious white oak was sawn into a 3/4 inch thick solid board, a certain number of square feet of flooring would be obtained. And now, attention! If this same log were used to produce thin veneer for engineered hardwood, 3 or 5 times more finished flooring could be obtained from it. This means that to cover the same area, 3 or 5 times fewer valuable trees need to be cut down. This makes engineered hardwood a much more environmentally responsible choice. Every year, over 25 billion square feet of oriented strand board are produced worldwide. Imagine, this amount would be enough to cover the entire state of Delaware. Twice. Or to build a path around the Earth over 190 times. Plywood was once the king of the market, but the 80s changed everything. And today, OSB controls over 75% of American construction. But how is a material that changed the industry forever, born from young trees, through hot baths, giant graters, and infernal presses? Watch closely. At the end, you'll learn a secret that even builders keep quiet about. It all begins not in a waste warehouse, but in the forest. For the production of high-quality oriented strand board, preference is given not to random offcuts, but to whole logs, usually from relatively young, fast-growing trees like aspen or southern yellow pine. These forests are often managed and self-sustaining, which makes the process more environmentally friendly. When the logs, tens of feet long, arrive at the factory, they are not immediately sent to the workshop. First, a hot bath awaits them. They are immersed in long pools of hot water, or placed in chambers where they are treated with steam. This isn't just washing. This process, which lasts several hours, softens the wood, and most importantly, weakens the bond between the wood and the bark. After this sauna, the logs go to a debarking machine. Imagine a huge rotating drum with protrusions inside. The logs rubbing against each other and against the walls of the drum, and the bark flies off them like a husk. Bark removal is a critically important step, as bark lacks strength and does not glue well, so it is an undesirable impurity in the final product. Annually, factories in North America produce over 25 billion square feet of oriented strand board. This number is so absurd that it's hard to comprehend. Let's try. If you took all this quantity of panels and laid them out, you could completely cover the entire territory of the state of Delaware. Twice. Or build a continuous 1-foot wide path that would wrap around the Earth at the equator over 190 times. This is not just a lot, it's total domination. For decades, plywood was the king of the market. But in the 80s and 90s, this daring newcomer came onto the scene, and today oriented strand board controls over 75% of the sheathing market for walls and roofs in residential construction in the United States. This was a real quiet revolution. The cleaned, light, and still damp trunks are ready for the main event, transformation into thousands of thin ribbons. They go to a machine called a strander, or a flaker. This is the heart of the whole process. Imagine a giant metal disc rotating at a frantic speed, equipped with dozens of sharp, scalpel-like knives. The log is slowly fed to this disc, and it shaves off long, flat, chip-like ribbons, strands. This is not chaotic shavings. Each strand has parameters precisely set by engineers. The length can reach 6 inches, the width, about an inch, and the thickness, only a few hundredths of an inch. It is this geometry, this noodle shape, that is the key to the future strength of the oriented strand board panel. When ordinary boards are made from a log, a significant part of it, up to 50%, turns into sawdust, offcuts, and shavings. And in the production of oriented strand board, from 85 to 95% of the entire wood of the log is used. We will talk about this later, but practically nothing goes to waste. The strands are cut from the entire length, and the bark, sawdust, and the smallest particles are burned in furnaces to provide energy for the factory itself. This makes this material not only cheaper, but also much more environmentally responsible. The resulting mass of wet, fresh chips, resembling a huge pile of light noodles, is stored in special bunkers, and from there, it is sent for drying. This is a huge, multi-story drum, slowly rotating, half a football field long. Inside it, a high temperature is maintained, and while the strands are slowly tumbling, moving from one end to the other, a stream of hot air evaporates the excess moisture from them. The moisture needs to be reduced from 50 or 70% to only 2 or 3%. This is absolutely necessary so that the resin can properly soak the wood and glue it firmly. After drying, the strands pass through a system of huge vibrating screens, which sift out particles that are too small, for example dust, which will go to fuel for the same dryer, and pieces that are too large, which will be sent for regrinding. Now the perfectly dry and sorted strands are ready for impregnation. They enter a huge, slowly rotating drum mixer. While they are being mixed, a sticky chemical cocktail is sprayed onto them through special nozzles. The main ingredient is a waterproof resin, which will be our glue. The second important component is paraffin wax. It envelops each chip like an invisible raincoat, and it is this that will give the future-oriented strand board panel its famous moisture resistance. And now, the smartest and most important part of the process begins, which gave the material its name: orientation. The strands, impregnated with glue and wax, go to a long, wide-forming conveyor. Here, a whole system of mechanical choreographers works. Special discs, rollers, and combs that lay out the chips in a precisely defined order. First, the bottom layer is formed. The choreographers lay out the strands so that they all lie parallel to the long edge of the future panel, that is, lengthwise. Then comes the turn of the middle layer. Here the strands are laid out perpendicularly, that is, crosswise. And finally, the top layer is again laid out lengthwise. As a result, we get a thick, fluffy, 3-layer pie, where the fibers in each layer are perpendicular to the fibers in the adjacent one. It is this cross structure, which imitates the strength of plywood, that is the secret that makes oriented strand board incredibly strong in bending and resistant to deformation. This fluffy mat, which can be several feet thick, slowly moves to the final test, the hot press. This is a real industrial leviathan, a multi-story structure that creates colossal pressure and heat. The mat enters inside, and massive steel plates begin to compress it with a force of hundreds of pounds per square inch. At the same time, the press is heated to a temperature of 400 degrees Fahrenheit. This heat activates the resin, causing it to polymerize and permanently glue all the chips into a single monolithic shield. The wax also melts, even better impregnating the wood and filling microscopic voids. In a few minutes, the loose mass turns into a hard, incredibly dense and hot panel. A huge master sheet comes out of the press, which can be 50 feet long and 12 feet wide. While it is still warm, its edges are trimmed with diamond saws, and then giant saws cut it into standard building formats, most often 4 by 8 feet. Markings with information about its thickness, class, and compliance with building codes are applied to the surface of the panel. Sometimes special tongues and grooves are cut into the edges so that the sheets fit together perfectly when installing a floor or roof. The finished, perfectly rectangular sheets are stacked in high piles by robotic manipulators, wrapped in protective film, and sent to the warehouse. And so, having passed the path from a whole log through a giant grater, a sticky shower, and the fiery embrace of a press, this honest, unpretentious, and insanely strong material is born, ready to become the silent but reliable foundation for thousands of homes across the country. For the construction of an average single-family home with an area of 2,400 square feet, approximately 8,000 square feet of oriented strand board panels are needed. This material goes into everything. They sheathe the exterior walls, creating a strong and rigid frame. They make a solid sheathing on the roof, on which shingles are then laid. And of course, they make the subfloor, which is the foundation for all rooms. In essence, the entire modern American house is a wooden frame wrapped in a strong cocoon of oriented strand board. Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills, where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, this scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that, at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. A special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles.